Hello class, welcome to today's lesson 2.11 in which we're gonna go over the topic of transformations of graphs. And we're gonna investigate three types of transformations: translations, also known as shifting, reflections, and stretches. There are many more types of transformations, but we're not gonna look at them. So let's start. I'm gonna start with this question. Let's start very simply and with an equation, or more, or better, with a function that we know very well. Let's suppose we take the function f of x equals x squared and we want to graph this function. Okay, what do we do? Well, remember, you come up with this table, you give some values to x, and you get the corresponding values of f of x, which I'm also calling y, in order for them to be represented in the y-axis, right? That's why I'm saying that f of x is also equal to y. And well, you do this very quickly. You can give 0 and you get 0 in here. You can give 1 to the x, f of x is going to be 1. You can give -1 to x, and f of x will be 1 also, right? Because it's -1 to the square. And you do this for several of them. I'm just gonna do it for this set, and I'm gonna have this, right? This is a number 4. Okay, and then you go over the Cartesian plane and you plot these points. So it's 0, 0, 1, 1, 2, 4, 3, 9, and basically those same points on the other side, right? The reflection. Okay, perfect. And then you trace smoothly the graph of this function, which is going to be a parabola. I'm doing my best. There you go, more or less. Okay, perfect. So we know how to do this. Very simple. Okay, so what? Okay, now the question is this. Now that I know how the graph of this particular function looks, okay, which is a very, if you notice, this is the simplest case of the quadratic function, right? Because it has no coefficients in regards to b and c. The coefficient of x squared is just 1, etc. Okay, so this is the simplest version of what we understand by the quadratic function, the simplest one. Now, what if I give you another function? I'm gonna call it h of x, and this function, I'm gonna define it as being equal to f of x plus another number, let's say 2. Okay, h of x is going to be equal to f of x plus 2. So basically, h of x is the same as f of x, save for this little inclusion of this coefficient. You see? Let's see what happens when I graph when I draw the graph of this function h in the same Cartesian plane as f is. This is f, okay? So let's start. First of all, h of x is going to be equal to x squared plus 2. Why? Because f of x, as given by this part, is equal to x squared. And then we do the same. I write x and then y equals h of x in this case, and I do the same type of analysis. I'm going to give the same numbers to x, 0 from 0 to -3. So let's start. It's going to be 0, 1, -1, 2, -2, 3, and -3. So what values am I going to get for h of x? Well, when x is 0, that's going to be 0 to the square, which is 0 plus 2. So I'm going to get 2, right? And then for x equals 1, I'm going to get 1 to the square, 1 plus 2, 3. And by doing the same, I'm going to complete the following table. It's going to be 2, 3, 3, and then it's going to be 6, and 6, right? Yes. And then it's going to be 11 and 11. Make sure that what I did is correct. Okay, I'm just evaluating the function h of x in these particular values, the same ones that I chose in here. And now let's graph the function of h. So it's going to be the point 0, 2, which is this one, and then the point 1, 3, which is this one, and then the point minus 1, 3, and then 2, 6, and then minus 2, 6, and then 3, 11. So it's going to be over here, and minus 3, 11. We trace the graph of the function as best as we can. It's kind of hard doing it with this drawing tablet. Okay. Yes. Okay, so you can see the, well, I could have done better here. You can see that the graph of h is basically, let me try to do that a little better. It's basically, guys, that's better. It's basically the same parabola as the graph of f, with the only difference that is displaced upwards. Can you see? This blue parabola is the same as this yellow one. It's exactly the same parabola. It has the same shape, the same size, whatever. The only difference is that it's displaced 2 units above the yellow one. Can you see? And if you notice, those 2 units are in fact the same distinction that we added here. That was the inclusion of that coefficient, you see, of that constant. H of x is basically the same as f plus 2. Okay, and we can see how that plus 2 affected the graph of h by basically being the same as the graph of f, but displaced upwards by 2 units. Can you see? Now, if we did this something similar, not the same, but something similar, if I come up with another function, which I may call g of x, and I decide that g of x is going to be the same as f of x, and now let me subtract minus, let's say 3, okay? And I do exactly the same thing. Exactly the same thing. I'm going to go like, okay, g of x is going to be then equal to x to the square minus 3. And then I'm going to plot x and and here I'm going to draw y equals g of x. And I do the same thing, 0, 1, minus 1, 2, minus 2, 3, and minus 3. What values are you going to get for g of x? When x is 0, this is going to be minus 3. When x is 1, this is going to be minus 2, minus 2. And then for 2, you're going to get 1 and 1. And for 3 and minus 3, you're going to get 6 and 6. Am I right? Yes, okay, for all of them. And then you're going to plot these values or these points over the Cartesian plane. Let's do it very quickly. We have 0, minus 3, it's this point. And then 1, minus 2, which is this. And then minus 1, minus 2. So it's done, done, done. 2, 1, which is this one. Done. Minus 2, 1, which is this one. Done. And then 3, 6, which is this one. And minus 3, 6, which is this point. So done and done. We trace as best as we can. And if you notice, what you're gonna get is, one more time, the same shape as before, the same parabola as the yellow one and as the blue one, but in this case, in reference to the yellow one, which is my original function, so to speak, the red parabola now is displaced 3 units below. Okay, so g being the same as f, but with the inclusion of this new coefficient over here, this new constant, then the graph of G is basically the same as the graph of F, only that displaced downwards or shifted downwards by 3 units. You see? So what are we doing, guys? What pattern are we seeing? That if you modify, if you know the, let me do it in white. Okay, if you know how the graph of a function f looks, it doesn't, and by the way, it doesn't matter how complex the function is. If you know this graph, then the graph of this other function f of x plus a constant c will be the same as this one, with the only difference that this one is going to be displaced upwards by c units. Okay, just like the blue one. Okay, this is displaced with reference to the yellow one. This is displaced 2 units upwards, and the graph of a function f of x plus minus c, or which is the same f of x minus c, right? It's the same. Then the graph of this other function is going to be the same as the graph of f. It's going to look exactly the same, only displaced downwards by c units. Just like this red parabola is displaced 3 units, you see the negative sign, with respect to the original, let's say, parent graph, which is this. Okay, so that's the idea, guys. In regards to translations, this is what is known as translation. We say that the blue parabola is translated or shifted 3 units with respect to the original function f, and the red parabola is shifted minus 3 units with respect to the original function f, which is in yellow. So that's the idea behind translations. Now, you may be thinking, does this apply to any type of function? Yes, and as a demonstration, I mean, I already told you about that in here, but if you want me to convince you even more, let's look at this function. Okay, in here we have the function f of x equals x to the cube. It's the cubic function, and it looks like so. Okay, get used to it. You have to get used to the shapes of the functions. This looks like some sort of S. Okay, and looking here, I'm giving you another two functions, g of x and h of x. And if you notice, g of x is the same as f of x, right? Because f of x is equal to x to the cube, with the inclusion of another constant, which is plus 1/2. So when I graph this function in a moment, when I push this button, this function should be the same as this one. Okay, it should look in the same way, with the only difference that is going to be displaced upwards by just 1/2 of a unit. So let's do it. There it is. Can you see? This is the unit number 2, this is the unit number 1, and this is the unit 1/2. So as we can see, the graph of this function, which is g, the blue one, is the same as the one before, as my original function, which is f, with the only difference that it's displaced upwards by 1/2. You see, you can see there the 0.5. Okay, now I'm going to erase it. Now look at h. H of x is equal to x to the cube minus 7. So that means that h of x is equal to f of x minus 7. Another inclusion of a constant, in this case negative. So what you're going to observe is that the graph of h, once I graph it, is going to look in the same way as f, only displaced downwards by 7 units. Let's do it. Can you see? I'm going to zoom out. You see? It's the same shape. This one and this one are exactly the same shape, the same size, everything, except for the relative position, right? This one, the new transformed graph, is downwards by 7 units with respect to your original function. You see? So this is how translations or shiftings work. So some of you may be thinking, can we do the same? Can we create a function g such that it's equal to something related to f, so that now the function of g will be either shifted to the left, okay, being the same as this one, or to the right. You see what I mean? Okay, so let's see. Can we answer that question in the positive? Yes. And now the change that we have to do to the original function, it's not an addition over here, okay? Like in so. It's not gonna be f of x plus or minus something. The inclusion of the constant that we're gonna do in order to achieve what we want to do is inside the very same variable. Let me tell you what I mean by that. Instead of x, instead of x squared, okay, f of x is equal to x squared. Instead of x squared, I'm gonna write this, x minus 2 to the square, okay? And as you can see, the graph of this new function g is actually shifted to the right by how many units? By 2 units. Can you see? The vertex of the original function goes from 0 and the transformed graph goes to 2. So this new function, which is g, is shifted to the right 2 units with respect to the original parent function, which is f. And how did we achieve that? By doing this, guys. If f of x is equal to x squared, then what I'm gonna do is either add or subtract a constant, but inside the very same variable, okay, inside of there. I'm gonna change x by x minus 2 in this case, in order to produce this phenomenon, shifting towards the right. Now, if I do this instead, h of x equals x plus 2 to the square, what do you think is going to happen? Shifting to the left. You see? This is shifting to the left. By adding a constant of 2 units to the x, the graph of the function is being shifted to the left. And by adding, by subtracting 2 units from the variable itself, and then raising it to the square, we get this, shifting to the right. Okay? So, is that going to work for all possible functions? Yes. Any function, it doesn't matter. Let me create a function, f of x equals x to the cube. That's my original function. I'm going to call it my parent function in its most simple form. And then I'm going to create 2 other functions, which I want them to look just like f, just like this, but shifted either to the right or to the left. If I want to shift to the right, what I'm going to do is write the same function, but I'm going to subtract 3 to the variable, x minus 3 to the cube. And you can see that the new graph is going to be shifted with respect to the original one by 3 units. Can you look at this 0 and look at this 3? You see? So it's shifted 3 units towards the right by subtracting 3. If I create another function, h of x, and I want h to look just like f, but shifted towards the left by 3 units, I'm going to add to the variable x 3 units, and then raise also to the cube. You see? And we get shifting towards the left. And it doesn't matter what function you come up with. It doesn't make any difference. F of x equals e to the x. That's my original function, or my parent function, in its simplest form. And now that I know that, I can create a function and call it g, or whatever. And if I want g to look just like this, but shifted towards the right, I'm gonna subtract from the variable two units or whatever number of units. Let's subtract 4, x minus 4. Okay, I'm subtracting from the variable 4 units, and as you can see, this new graph is shifted towards the right with respect to the original function by 4 units. Okay, and if I want to do the opposite, like shifting to the left, I'm gonna need to add 4 units to my variable x, and we get this new shifting, okay, by 4 units. How do you know it's 4 units? Well, look at this point, okay, it's 0, 1. So the same point corresponding to the other function would be this, and you can see it's 0, I'm sorry, for 0, 1, and this is 4, 1. You see? So it's displaced by 4 units towards the right, and this point is displaced by 4 units towards the left. You see? So you can see, in fact, that we're talking about displacement by 4 units, either to the right or to the left. So that's how this works. So just make sure, do not confuse. I mean, the source of confusion here can be the following: that you want to match or to relate shifting towards the left with the negative, with the subtraction of a constant to the variable. No, it's the opposite. Okay, and this is the proof. If you want to shift towards the left, you're gonna add to the variable. If you want shifting towards the right with respect to your original function, you're gonna subtract from the variable. So this is how translations works, or shiftings. Okay, it's the same. Translation, vertical translation, horizontal translation, and vertical shifting or horizontal shifting. They mean the same. So that's it, guys. And in the next lesson, we're gonna continue with reflections and stretches.